Okay, so based on the description we have just seen, can we come up with an algorithm that will solve the matrix chain multiplication problem? The answer, of course, is yes. This is the algorithm. Okay. Now the algorithm actually is going to use two arrays. In addition to the array M, the algorithm also compute an array S. Let me just show you those two arrays. So in addition to solving the subproblems, so this gives us the minimum cost, but we also need to be saving the values of k, that give us those optimal solution, and that is what we are saving in the second array S. Okay, so very similar to what we did in rod cutting problem, because eventually we are interested not only in what is the minimal cost, what is the minimum number of scalar multiplication, but we want to know at what point do you put the parenthesis so that you get the minimal cost. To be able to do that, we need to be saving our values of k as well, okay, in this array S. Okay, so this is our matrix chain multiplication algorithm that try to solve using DP, this time using the bottom-up approach, starting with the smaller problem first and saving them in the table. Okay, the input to the algorithm is the array of matrix dimensions. So this P is an array of matrices. It's an array of the dimension of the matrices P0, P1, P2, and so on until Pn. Okay. Okay, so the first thing the algorithm does is it computes n. Okay, n is the size of this array minus 1. Why minus 1? Because here, if you remember, we included 0. Okay, from P0 until Pn. So actually our length is just the length of P minus 1. Okay, this is the maximum chain you're going to have. In terms of the number of matrices involved in the chain, they are just n. The dimension is always going to be 1 more than the actual number of matrices because we are starting from 0. Okay, next we define two arrays, M. Okay, so M is going to be of dimension 1 to n, 1 to n. Okay, 1 to n, 1 to n. But S doesn't need to go as far as n, because as you recall, if it is if I is equal to j, then it is only one matrix involved, and therefore k doesn't be, we don't need a k in this case because there is no splitting involved. So we're gonna have I to vary only from 1 to n minus 1 in the case of array S, and j to varies from 2, not from 1, from 2 to n. Okay, all right. So once you define these two arrays, the first thing is to fill in the bottom row because they are all going to be zeros. Those chains of length 1, the minimum cost is 0. So we are saying for I from 1 to n, store 0 in MII. Okay. Next, we now start in increasing number of length or increasing size of length. Okay, starting with those matrix chain of length 2, length 3, and so on until length n. Okay. Now, how do we compute the problems? As we said, we're going to vary I from bottom to top, but also from left to right. We start a loop that starts based on the length of the chain. For L from 2 to n, we have already taken care of those of length 1 here. Now from length 2 until length n. Okay, what do we do in each case? For I from 1 until n minus L plus 1. Okay, until n minus the length plus 1. Okay, and initialize j to be equal to I plus L minus 1. Okay, good. Now initialize mij to be infinity, because remember we're trying to look for the minimum. So let the initial value be as maximum as possible, so that if you later find a smaller value, you will update. Okay, good. So this is our initial value of mij. Now we need to vary our k. And remember, k varies from I until j minus 1. Alright, so for each value of k, we just follow our formula. Compute q to be mik plus mk plus 1 j plus pi minus 1 pk pj. This is exactly from our formula. So this will compute one of the q's. But is it the minimum? We don't know. So we have to compare it. If this q is less than our current value of m, then store the q in our mij, update the mij, and also store the k in the matrix Sij. This is basically the algorithm that will fill this table in a bottom-up manner based on the length. So starting from the bottom, and also for each row we're going to do it left to right. This is exactly what this algorithm will do. Now in terms of the efficiency of the algorithm, you can see that it is actually just big O of n cubed, because it's just a sequence of nested loop, 3 times nested, 1 2 3. So in the worst case it's going to be n cubed. This is tremendous if you compare it with the exponential that you're going to get if you just try to implement the algorithm using divide and conquer. So the problem has been reduced from exponential to polynomial of degree 3. Tremendous. Okay, in order to make this algorithm more clearer, we are going to take a concrete example to see how it works. Okay, suppose you are given a chain of 4 matrices A1, A2, A3, and A4 of dimensions P not equal to 5, P1 equal to 4, P2 equal to 6, P3 equal to 2, and P4 equal to 7. So we are given the dimensions of these matrices. A1, for example, is 5 by 4. A2 is 4 by 6. A3 is 6 by 2. And finally, A4 is 2 by 7. So given this dimension, find M14. In other words, find the minimum number of scalar multiplication needed to multiply these 4 matrices. Okay, so according to our algorithm, we need to solve the subproblems involved in increasing length, starting with those of length 0. Okay, for those of length 0, I and j are equal. So basically just the bottom row that you can see here, which means actually we are concerned with only one matrix, and in that case the number of scalar multiplication involved is 0. So just fill this table with 0. I mean this row with 0. Okay, next is to consider those of length 1. Subproblems of length 1 in this example are only 1, 2, 2, 3, and 3, 4. As you can see here, why the subproblem is of length 1? Because k can only have one value, which is 1 in this case. Remember, k can vary from I until j minus 1. Well, j minus 1 in this case is going to be 1. So k can only be 1. Similarly, here k can only be 2. And here k can only be 3. So these are the 3 possible problems of length 1. And these are the ones we need to solve next. After solving length 0, then length 1. Okay, so here we go. According to our formula, M12 is the minimum of M1k plus mk plus 1, 2 plus p naught, the naught is obtained from I minus 1, pk and pj, well j is 2. Okay, varying k from 1 until just less than 2. So actually, as we said, there is only one possible value for k, and that is 1. K is equal to 1. So actually, there is only one value in this set, and it is M11 plus M22 plus P0 times P1 times P2. Well, M11 we already computed it. It is 0. This is 1, 1. And so also M22. 2 is 0. So just read the values from the table and they're going to be 0. Okay. So 0 plus 0 plus, what is this? P0 is 5, as you can see here. P0 is 5 times P1 is 4 times P2. Okay, P2 is 6. So if you multiply 5 by 4 by 6, you're going to get 120. 5 times 4, 20. 20 times 6, 120. And put 120. Okay. What is the value of k that gives us this value? Is 1. So go to the other array and store 1 in position 1, 2. Okay, so the k value for 1, 2 for this array is 1. Okay, next we're going to consider the next problem of size 1, which is M23. M23, this one. Okay, for M23, the only possible value of k is 2. And therefore, if you substitute it, this is what you have. So again, you will see that M22 and M33, they are all zeros. So actually, all you need is this product. P1, which is 4, times P2, which is 6, times P3, which is 2. Multiply this and you get 48. It is this 48 that you should put in position 2, 3. Okay, what value of k gives you this value? It is k equal to 2. So store 2 in the other array S at this position, 2, 3. Okay, next we look at M34. Okay, so for M34, this is what you have. K obviously can only be 3, because it has start from I. It cannot be up to 4, so its only possible value is 3. So if you substitute k as 3 in this formula, you will see that we have M33 plus M44, k plus 1 will be 4, so M44 plus P2, PK, P4. PK is P3, so P2, P3, P4. So yet again, these values are zeros. Okay, M33 is 0, and so also M44 is 0. So all we need to worry about is P2 times P3 times P4. P2, P3, P4. 6 times 2 times 7. So 84 will be stored there. The value of k is 3. So that's what you have there. Good. So we have solved all the problems of length 1. Next is to solve problems of length 2. Now, these are the possible problems of length 2. M13 and M24 in this particular example. Okay, so you can see here K can be either 1 or 2, whereas here K can be either 2 or 3. This is why the problem is of length 2. Okay, so here we have two options to take a minimum, not like the previous one where the length is only 1, and therefore it is the minimum by the default. So let us proceed, starting with 1-3. For 1-3, we have to vary K from 1 to 2. Okay, so if K is 1, then we will have 1, 1 plus 1 plus 1 is 2, so 2, 3 plus P0, P1, P3. Okay, if K is 2, we will have 1, 2, okay, plus M 3, 3 plus P0, P2, P3. Notice that the P0s are going to be the same as the P0 for the I, and the P3 are also going to be just the PJs. Okay, so the first one here is just P of I minus 1, which is 0. And the last for P here is P of J. The middle one is K. So if K is 1, you will have PK. Okay, if K is 2, you have P2, and so on. Now, if you compute these values based on the result we have, 1, 1 is obviously 0. But what about M23? M23 is 48. Okay, so we have 0 plus 48 plus the product that you're going to get by multiplying P0, P1, P3. If you do that, you will see that you will have 88. Okay, what about the other one? M12. Okay, 1, 2 is 120. M33 is 0, so 120 plus the product you're going to get if you multiply P0, P2, P3. If you do that, you see that you're going to get 180. The question is, which of these two values is the smallest? Obviously, 88 is the smallest. So it is 88 that you should put in position 1, 3. Okay. And the next question is, what value of K gives you this minimum value? Was it K equal to 1 or K equal to 2? Obviously, it was K equal to 1. So it is K equal to 1 that gives you the minimum. So you store 1 in the array S. Next is M24. So here again, K will vary from 2 to 4, to 3 rather, because it cannot be up to J. So the possible values for K are 2 and 3. Okay, so substituting in the general formula, it means you have again two options. And reading the values from your table, you will, as we did in the last slides, you will have 258 for the first one and 104 for the second one. The second one in this case is the minimum, for which K is 3. So you store those values, 104 for the actual minimum and 3 for the value of K that give you that minimum. Okay, so these are the two problems of size 2 that you have in this case. Last is the one that has length 3, which is the real problem we are trying to solve, the one for itself. Okay, that's the one we have in the next slide. So for 1, 4, which is of length 3, we have 3 options to consider and find the minimum, with K equal to 1, K equal to 2, and K equal to 3. Okay, so this is our general formula. If k is 1, you will have 1 1 plus m24 plus p0 p1 p4. If k is 2, you will have 1 2 plus m34 plus p0 p2 p4. And the last one, if k is 3, you will have m13 plus m3 plus 1, which is 4, so m44 plus p0 p3 p4. All these values, they are already computed in our table. Okay, 1 1, obviously the i's, they are all zeros. Okay, now what is 2 4? 2 4 is 104, and 1 2 1 2 is 120, and 1 3 1 3 is 88. So as we saw at the beginning, actually all we need are the values in this row and the values in these columns, okay, to compute the different options. So once you compute the different options, you see that there are 244, 288, and 158. Which of them is the minimum? Of course, the last one, 158. So the minimum value is 158. This is the minimum cost for our overall problem of multiplying the 4 matrices of the dimension that we are given. It's 154. Okay, the value of k for this particular subproblem is 3. Okay, so this is basically how the algorithm we saw about DP, the bottom up, how it will fill those tables to tell us the minimum. However, as we know, finding the minimum is not only our problem. We want to know where do we put the brackets if we want to solve the problem with minimum cost. So we need to go all the way to step number 4, construct the optimal solution. All right, so like the rod cut example, the optimal value m1n only gives the minimal number of scalar multiplication needed in a matrix chain multiplication, as I just said. To know how to actually multiply the matrices to get the minimal value, the array S that records the values of k for each optimal choice of I and j must be used. Okay, we call Sij is the value of k that gives you the optimal solution when you split the product ai to j into 2, okay, between ak and ak plus 1. Okay, it's a note, the array S only need to record the value of k for which the choice was made. Okay, because there is no splitting when I is equal to 1. This is why we didn't need to fill the bottom row for the array S. Okay, so now how do we construct the solution based on our array S? The following shows both the array M and S for the example we solved in the last few slides. Okay, this is the final solution. And we're going to see how to use the array S to construct the optimal solution. And that's how to find where to put the parentheses. So the following recursive algorithm prints the parenthesized sequence using the array S. This is the algorithm that we're going to use to actually print the parentheses. Okay, so it's called print optimal parents, meaning print the optimal parentheses. The input for the algorithm is the array S and I and J. Okay, for which subproblem are you trying to print the parentheses? Obviously, initially this will be 1n, n, where 1 is the first value of I and n is the last value of j. Okay, it will be making a recursive call, so these values will be changing as the algorithm call itself. Okay, so this is our array S, and we're going to use it to try and show how this algorithm works, basically by tracing the recursive tree. If you notice, the algorithm says if I is equal to j, there is nothing to do, just print AI. Otherwise, do a recursive call from S, for S, from I to K, because actually, if you remember what we are storing in Sij is the K. Okay, so if you come in with I to J, we're going to do two recursive calls. One from I to K. Okay, K, we're going to obtain it by going through this array. Sij will give us the K. Okay, and then another recursive call from a K plus 1. So this is the K, Sij plus 1 until J. Okay, so do these two recursive call. Before the recursive call, of course, we will always print the opening bracket and closing bracket. Okay, so we'll see that tracing the recursive tree of this algorithm will actually tell us where to put the parentheses. Okay, suppose we call this procedure with this our array S, and with initial value of I as 1 and j as 4. Okay, obviously I is not equal to j initially. Okay, here I'm just saying this 1 4, the corresponding value in our array S 1 4 is actually 3, so k is equal to 3 for this particular code. Okay, so that's the meaning of k. So if we go through, if we make a call with these values, obviously I is not equal to j, so it will not do the if part. It will go to the else part. Now in the else part, there are 4 statements involved. So if you are drawing a recursive tree, normally you will draw a branch for each of the 4 statements. Therefore, there is a branch that will just print opening parentheses, as you can see here. There is a branch that will make a call with the same S, okay, the same I, so I is still 1, but with the third argument to be Sij. And as we said, Sij for the first call is actually K, which is 3. So we're going to do a call from 1 to 3, and then a call from 4, okay, to 4, because the last value of the value of j is 4. So the third call is from 4 to 4, basically k plus 1, okay, to j, and j is 4. And the last statement in that particular call is to print a closing parenthesis. Okay, good. But this is a recursive call, so we're going to start all over, making a call with the same S, but this time with 1 3. So what is the value of k for 1 3? It is 1, so k is equal to 1. So again here, I is not equal to j, so it will not do the if part. Rather, it will make 4 different calls. First call will print opening parenthesis. Then it will call until k, so 1 to 1. Okay, and then it will call from k plus 1 to 3. So basically 2 to 3. Okay, the value of k at 2 3 is 2. We're going to need it for the next call. So 2 3, as you can see, is 2. Finally, it will do the last call, which will print a closing parenthesis. Okay, Before we come back to this call, let us see each of these other calls, what it will do. Clearly here, I is equal to j. So the algorithm simply say print AI. Well, I is 1, so print A1. So this is our first matrix that will be printed. Okay. But this call, I is not equal to j, so it's going to require actually 4 different calls. Print the opening, make another call, and then print the closing. So we will have print the opening, make a call with 2k, well, k is 2, so 2, 2. Make another call with k plus 1, which is going to be 3, so 3, 3. Okay, and then make a call to print the closing parenthesis. Okay, now this call will print A2 because I is equal to j, so it will just say print AI. Well, I is 2, so it will print A2. Similarly, this one will print A3. Okay, so the last recursive call we're going to go and do is this one, but here also I is equal to j, so it will just simply print A4. Okay, in other words, this is how the parenthesization will be done in order to obtain the minimal cost. Opening bracket, A1, as you can see here, then opening bracket, then A2, then A3, then closing bracket, then A4, then closing bracket. So this is what is meant by constructing the optimal solution. In other words, specifying where do we actually put the parentheses so that we get the optimal solution. We do that just with the help of the array S. Okay, so in this remaining part of the lecture, we are going to look at Memoized version of our solution to the matrix chain multiplication problem. It says, as with the rod cutting problem, the Memoized solution is always available as an alternative to the top-down approach. Okay, for this, we only need to directly implement the recursive DC solution and then see how we can improve it by saving solutions to subproblems in an array and looking them up if they are encountered again. So you're going to see on the right hand side the direct recursive algorithm to our problem using just divide and conquer, which is an ordinary recursive algorithm based on the formula we already derived. Okay, so this is the recursive matrix chain. It receives the array of dimensions and ij. So obviously if I is equal to j, I return 0 because there is no chain involved with just one matrix. Otherwise, define a variable mean to be equal to infinity, and then in a loop for k from 1 to j minus 1 according to our formula, compute q to be a recursive call from I to k plus a recursive call from k plus 1 to j plus the product pi minus 1 pk pj. So exactly as in our formula, but compare this q with the current value of m. If q is less than min, then min becomes q. Okay, and you repeat. So by the end of this loop, return the minimum that you're gonna get. This is a very simple recursive algorithm that will solve the original recursive solution that we derived. But obviously this is going to be exponential in terms of its operation. Question is, how can we improve this recursive algorithm? By introducing an array to store previous result, so that when we encounter a similar problem, we just read the result from the array. This is basically what Memoized version involves. You use the same recursive algorithm, just modify it to include memoization, meaning to introduce an array that will allow you to remember previous solutions. Okay, so this is the Memoized version. It normally involves breaking the algorithm into two. One part will just initialize an array. So this is the one to receive just the array of dimension, compute n, the length of the chain. Okay, it's going to be one less than the actual array of dimension, because as we said, the array of dimension has an extra one value for the p naught. Okay, define an array m of length n by n, so 1 to n, 1 to n. Okay, notice here we are deliberately defining only the array m, not the array s, because you're going to be asked to do a modification that will also introduce the array s as an exercise. Okay, so here we are only concerned with the minimum values, not where we got those minimum values. Okay, so initialize the array, the 2D array that you just created, with infinities. So the maximum possible value that you can have, initialize the array with those values. That is all this first algorithm will do. Now it will call the other algorithm, which we call lookup chain, passing it to it 4 arguments. The array that has just been created, array m, p, the array of dimensions of the matrices, and of course the initial value of I is 1, and the initial value of j is n. So 1n. Alright, now let's look at the lookup chain algorithm, and you see that it is very minor modification to the recursive algorithm that we saw in the last slide. So here it receives 4 arguments. We already explained them, m, p, I, and j. Now look here, the first thing this algorithm does is it checks, is mij, which we are trying to compute, has it been computed before? It will have been computed before if the value is less than infinity. Okay, so if it has been computed before, just return it. Don't do anything else. Read the value from the array and return it. Okay, but if it was not computed before, now we have to follow the algorithm as before. So first we check if I is equal to j. Then in this case there is nothing to do, just assign 0 to the cell and return it. Okay, so save it and then return it, not return directly. Save 0 in that cell and then return it. Okay, this will be one of the best case. Now what if I is not equal to j? Then in that case we have to do the recursive calls, and we have to do that in a loop, trying to compute the smallest value of q. So we need to run for k from 1 to j minus 1, do a recursive call from I to k, plus the result of the recursive call from k plus 1 to j, plus pij, pk, pj. Compute your q. Now, if this q is smaller than what is already in the array at this position ij, then update the value at ij with the new value. Otherwise, don't bother, just go and do another iteration. So by the end of this loop, we will have updated the value inside mij with the smallest value obtained from this loop. So having saved it, now return it. This is basically all that the Memoized version of the algorithm involves. It's just a minor modification to the recursive version. Okay. Now the following illustrate the operations of both the recursive and the Memoized procedures in terms of their running time. The recursive version is obviously exponential, it's clear. The Memoized version does a simple lookup for the green cells in the following tree. So even though there are many subproblems, the Memoized version will not repeat the calculation. It will just read them up from the table. Okay. Yeah. So that's what we said here. The Memoized version does a simple lookup for the green calls. There are theta of n squared distinct subproblems, and the Memoized procedure makes theta of n recursive calls to solve each of them. Therefore, a total number of running time will be big O of n cubed. N squared, total number of subproblems, plus what is needed to solve them. It's just a linear operation needed to solve each one of them. So overall, you have the running time to be big O of n cubed. So very similar to the running time of the bottom-up approach, which had 3 nested loops, and the big O there was also big O of n cubed. So the same thing here. Just look at the total number of subproblems and how much is involved in solving each one of them, and you end up with the same result. Okay, so that is the end of the discussion about that, our third example. Now, to summarize about dynamic programming generally, we're going to list its 2 main elements, discuss how to normally go about solving dynamic programming just as a summary, and also how to find its running time. So 2 key ingredients of dynamic programming are: 1, optimal substructure. An optimal substructure, an optimal solution to a problem that contains within it an optimal solution to subproblem. This is how we define an optimal substructure. Okay, so the first thing you do when you are trying to solve a problem using dynamic programming actually is try to come up with this optimal substructure. Okay, optimal solution to the entire problem is built in a bottom-up manner from optimal solution to subproblem. This is the idea of optimal substructure. If you can characterize your problem in terms of optimal solution, then you are on your way to solving the problem using dynamic programming. The other key ingredient for you to be able to apply DP is to make sure your recursive version involve overlapping subproblems. Okay, in a recursive algorithm, if a recursive algorithm revisits the same subproblems over and over again, then it means the problem has overlapping subproblem, and therefore is a candidate for solving using dynamic programming approach. These are the 2 key ingredients that you must observe if you are to solve a problem using dynamic programming. They must exist, yani. So how do you find optimal substructure? Okay, usually what you need to do is to show that a solution to the problem consists of making a choice, and that choice will result in 1 or more subproblems. Okay, for example, in the rod cutting problem, we saw that the solution involved making a cut. Okay, so choosing a cutting position will allow you to come up with an optimal substructure. Okay, in the example we just saw about matrix chain multiplication, the choice here is where to put the parentheses. So choosing an index at which to split the matrix chain. Okay, so usually you need to find that place where you will create subproblems. Okay, or you divide a problem into subproblems. Okay, now suppose you are giving a choice that will lead to an optimal solution. You don't try to find the value of that particular choice that give you the optimal solution yet. Okay, you try initially to see how you can solve the problem by looking at all the possible choices. Okay, and then apply dynamic programming technique to reduce those number of choices. This is the idea. Okay, determine which subproblems follow and how to characterize the resulting space of subproblems, usually ordering them in order from the smallest to the largest, so that you can utilize, for example, the bottom-up approach. Yeah. Okay. Now, you need to also show that the solution to the subproblem has the optimal substructure property. And this can easily be done using a cut and paste proof by contradiction technique. Okay, just assume you have another optimal solution to the subproblem, paste it in the original solution, and you see that you have a contradiction. So it's usually easy to prove that the structure that you came up with is actually an optimal substructure. Okay. Now, optimal substructures can vary in two different ways, and both are important point to note if you are trying to solve a problem using DP. Okay. First is, how many subproblems are there? How many subproblems? Okay. Okay. In the rod cutting problem, one subproblem of size n minus I for each choice of a cutting position. Remember, once we decide this is the position I we're going to cut, we assume the left-hand side is not going to be cut anymore. So in that case, we were left with only one subproblem on the right to solve. Okay, in matrix chain multiplication, however, we were having two subproblems for each choice of the splitting index k. So for each k you choose, you will have two subproblems, one on the left, one on the right. Okay, so there are cases where you can reduce it to just one problem, as we saw in the rod cutting problem. But there are cases where your choice will actually involve two subproblems, and there is no easy way to reduce them to a single subproblem. Okay, so this is one issue, how to find the how many subproblems. The next question is, how many choices do you have? How many choices? In the rod cutting, there are n choices for I in order to determine which one will yield an optimal solution. Okay, you have to check all the n possible cases. For the matrix chain multiplication, however, we have j minus I choices for each index k at which to split the product. So again, this depends on the problem you are solving. How many subproblems are there, and then how many choices do you have? Okay. These two things that we just discussed, the number of subproblems and the number of choices, usually helps you to determine the running time of the algorithm that you'll come up with. Okay, the running time is usually the number of subproblems times the number of choices. So for example, in the rod cutting, there are big O of n number of subproblems and big O of n number of choices. So overall the running time is big O of n squared. For the matrix chain, on the other hand, there are big O of n squared number of subproblems. So the overall running time is big O of n cubed. Usually you also have another option to determine the running time, and that is by looking at the subproblem graph. Okay, as we remember, each vertex of a subproblem graph corresponds to one subproblem, and the choices for a subproblem are the edges that are incident to that subproblem. So multiply these two and you will get the overall running time of the problem. So for the rat cutting, the subproblem graph had n vertices and at most n edges per vertex, and that yield again n squared. Okay, so this is another way to find the running time. For the matrix chain multiplication, if we were to draw the subproblem graph, it will have n square vertices because there are n square subproblems, and each vertex will have a degree of at most n, or n minus 1, so giving a total of n cubed vertices. So again, if you multiply, you will get big O of n cubed. Yeah, so these are the two different ways you can determine the running time of a DP program, either by multiplying the number of subproblems to the number of choices, okay, or by using a subgraph. And that brings us to the end of our discussion. The last part is the exercises. These are from the book. The first one is saying find an optimal parenthesization of a matrix chain product whose sequence of dimension is given here. So this is P0, P1, P2, P3, P4, P5, and P6. Find the parenthesization needed. So here actually the question is not finding the minimum number of scalar multiplication needed, but also telling us where to put the parentheses. So you have to construct the solution as we did in the example. Okay. The second one says give a recursive algorithm called matrix chain multiply that will take an array A, an array S, and then I and J that actually perform the optimal matrix chain multiplication given the sequence of matrices A1, A2, and so on until AN. So this array A actually is array of matrices, matrix A1, matrix A2, and so on until matrix N. And an array S telling us where best to do the cut, okay, or where first to do parenthesize the sequence, and then I and J that will actually do the matrix chain multiplication. Okay, the table, the S table computed by matrix chain order, and the matrix indices I and J, yeah, basically telling what the S and I and J here are. Okay, the initial call to this matrix chain multiplication algorithm is AS1N. So the first value of I is 1 and the first value of J is N. Okay, this is the procedure I given. We already saw actually the procedure that can do the matrix chain multiplication. If we are given two matrices, so all we are trying to do is to generalize it to do the multiplication, not just sequentially, but based on the parenthesization information stored in the array S. This is what the question is about. The last part is what I hinted to you earlier. It says update the Memoized matrix chain algorithm and the lookup chain routine to also return the array S of splitting positions, meaning the cables. If you recall, that procedure didn't return the array S, it only returned the array M. Now we want you to update it to also return the array S. This is the end of this lecture. Thank you very much.